Welcome to Lecture 7. This is part 1, and we are going to talk about feed-forward neural networks. Okay? So we are going to start by defining single hidden layer neural networks or shallow neural networks. We have already seen a bit of it when we talked about sieves, nonlinear sieves in our previous lecture. Then I'm going to talk about activation functions and the universal approximation capability. The third topic will be estimation, and finally, how to select what we call the network architecture. Okay? These are the references, all of them and many others, and many papers that I will mention over the slides. They are all on our Google Drive folder. Please take a look. If you are interested on the topic, there are many resources, and I will be very happy to discuss with you about neural networks, either during our office hours or during our live meeting on Friday. So let's start with the shallow neural networks. Okay? So we observe a response variable y and a set of explanatory variables, or covariates, or controls, you name it, or input variables x, which is p-dimensional. Okay? And there is a unknown mapping between x and y. So y is f of x plus a random term u. F is nonlinear and is unknown, and our goal is to recover f. Okay? So frequently f is the expectation of y conditional on x, so such that this implies that the expectation of u given x is 0. Okay? And what we have a random sample of y and x's, and we would like to estimate f to predict y star, a new point, from a new x star. Okay, so basically y star will be our f of x star, assuming that we are not able to predict the random component, the u term. Okay. So how we are going to do that? We are going to approximate f by a sum of basis functions, exactly as we saw last week on our lecture about sieves. Okay, and so the input of these basis functions and affine transformations, a linear combination plus a shift of the input vector x. Okay? And s is a basis functions, and the unknown parameters are the betas, the and the gammas. Okay, that should be estimated. And the basis functions, as they are called, the activation functions, in the neural network jargon, theta is called the weights. The elements of theta are the weights, but they're just parameters to be learned. They're the parameters of these of the sieve expansion, and we have a nonlinear sieve. So we have the basis functions are defined in terms of parameters, the gammas. And then we have a linear combination of these basis functions, and this linear combination is defined by the parameters beta. Okay, and beta naught, which in econometrics is called the intercept, and this is also an intercept of the linear combination. In the neural network jargon, they are called bias. And basically this gamma naught j will shift the S curve to the left or to the right. Okay? And while this gamma j will control the slope of the function S. So examples of S: logistic on your left, hyperbolic tangent on your right, very similar. The logistics between 0 and 1, the hyperbolic tangents between -1 and 1, they are very similar. They are both universal approximators. They serve as a basis that will be dense to a much, a very general functional space. Okay? If you vary the parameter gamma, you see that you can make the higher the gamma, the steeper is the function. The lower is the gamma, the close to linearity you have. And this is an example in 3 dimensions for a bivariate input vector. Okay? So in general, but not always, this function S is called the squashing function. And the squashing function is the function that will be mapping from real numbers into a closed set A and B. A is less than B, and usually the limit when x goes to infinity, the limit of x is B, and the limit when x goes to minus infinity is A. So it has an S format, right? Some popular squashing functions, the Heaviside, the step functions, logistic, hyperbolic tangent, Gaussian sigmoid, cosine squasher, all of them. Basically, the most used ones, at least in the early days, are these 2. Okay? And more recently, a non-squashing function that had been actively being used is the ReLU, rectified linear units, which is basically nothing's happening until you reach a value of x, and then it's linear. Okay? Of course, you can define it as a max between 0 and gamma x minus gamma naught, right? It's the same thing, but x here is just the argument. Okay? And good news, this is also a very powerful basis function. As you're going to see, it has the property of being an universal approximator. So you can use linear combinations of ReLUs to approximate very general nonlinear functions. And another non-squashing activation function is the radial basis, which is basically kind of this bell shape of Gaussian distributions. Okay? So why neural networks? Why it's so popular? It has been very popular during some period, and it was like almost forgotten, and now it's kind of resurrected from the ashes. Basically, because of that theorem, universal approximation theorem, I mentioned that theorem when we were talking about sieves, that the feed-forward neural network with a single hidden layer with arbitrary squashing functions, so linear combinations of these squashing functions, can approximate any Borel measurable function from one finite dimension space to another to any desired degree of accuracy, provided sufficiently many hidden units are available. What the hidden units is the terms in the summation. Okay? And how big is the class of measurable functions? Contains all functions with at most countable discontinuity. So it's very, very flexible. Okay? And references many papers. These papers are all on our Google Drive folder if you want to look at it. They are papers about functional approximation. One important point, this has nothing to do with the human brain. Okay? This is pure math, is functional approximation. Okay? Like you have in Fourier series, Taylor expansions, Stone-Weierstrass theorem, polynomial expansions, and so on and so forth. Just very flexible class of approximating functions. Okay? And also a nice result that the same network that can approximate the function can approximate the derivatives of the function whenever they exist. And that's the kind of architecture. So these are what we call the input layer, so basically the variables entering the network. And then we have here the hidden layer, and the blue balls are the neurons, called neurons, and then you have the output layer. So the input layer is just the vector of explanatory variables. The hidden layer, that consists of a set of hidden units or hidden neurons, okay? And the output layer, which is the predicted value. But how it works, how will we map the formula on our first slide to that graph? Basically, at each unit, inputs are linearly combined. So what reaches this neuron here is the linear combination plus this drift of the inputs. Okay? Then it reaches the neuron, and then the neuron can be fired. That's kind of the jargon, because you're using this linear combination as an argument to this squashing function. So here, inside of this neuron, there's this squashing function, you enter that and it will map something that's continuous in the reals to something that can be bounded between A and B, if it's question functions, or if it's a ReLU, it can be 0 or just the same thing. Okay, and then that's what's going to exit the neuron, that nonlinear transformation of the inputs. And then what you're going to do, you're going to linearly combine these outputs. So basically what the neuron is one term in the sieve expansion. Each term of the sieve expansion in this neural network literature is called a neuron. We could have called them a comet, a planet, or whatever, okay, a spaceship. It's called a neuron, and a collection of neurons is a neural network. Simple as that. Connections with the human brain, I can see any. Okay? I think my brain is much more complex than this thing here. This is just functional approximation. And we can also look this as a matrix. If we stack the variables, if we stack the parameters, we define the big matrix X, the big parameter matrix gamma, we can write this X times gamma, so that's the matrix of the linear combinations of the inputs that will enter the neurons, and then we can define this matrix calligraphic O of X gamma being exactly the outputs of the hidden units. And therefore, the mapping, what we get outside, what exists in the network, is just a linear combinations of these outputs of the hidden units. So H, our mapping, is just calligraphic O times beta. Okay? That's the mathematical representation in matrix form of a neural network. And basically what this linear combination they are doing, you can write the linear combination as a hyperplane. So in 2 dimensions, it's just a line, okay, here, this line, that's defined by this vector, gamma x equal to gamma naught. Okay, so gamma will give the direction of this thing here. Gamma naught over norm of gamma is the distance that we have from the origin. Okay, so if you can have like 2 regions, on one side of the hyperplane, on the other side of the hyperplane, with many hyperplanes, we can define a recursive formula for the number of regions that we have. So a neural network, basically what's doing is like it's splitting your input space in several regions and putting kind of smooth transitions between each region with the logistic functions or the hyperbolic tangent, if you want. So it puts weights basically on each region. Okay? And how do you train that neural network? Basically, we look at errors and we choose a loss function and minimize the empirical risk. So our empirical risk usually is the sum of squared errors, okay? That we can write everything in vector format, like what you can see the loss formula on the slide, okay? And no analytical solution, so we have to do it by a numerical approach. We use gradient descent and its many variations, okay? It's a non-convex problem, so potentially is several local minima. We have to control for that. Highly over-parameterized. There are way too many parameters to estimate, so it's really important to regularize. So we must use some regularization, okay? And what's the gradient descent or stochastic gradient descent? We update at every iteration. The new vector of parameters is the previous one times a step that's proportional to the negative of the gradient. Okay, that's what's called the back propagation, another fancy name for something that it's known for centuries. Okay, and the root of optimization dates back to the Newton method. Okay, and as old as that, but people in neural network literature decide to call it back propagation, but it's basically the gradient method or the quasi Newton optimization method. Okay. This is all implemented in many of all the packages. This eta is the step length, the learning rate, and if you remember boosting, the idea is exactly the same, that you changing the parameters in the direction of a local minimum, and how fast you get to there depends on this learning rate. Okay? The stochastic gradient is very useful when you have gazillions of data. So instead of using all the data, in each iteration you just use mini batches. You go there and randomly pick part of your data, and each iteration you use a different subsample of the data. This can dramatically speed the process. Okay? We are talking about gazillions of data, not something that you're going to see frequently in economics or in finance unless you really go into high frequency. Okay, okay, so training, stochastic gradient, but we have to train something. And what are we going to train? So which kind of network? So we're still on shallow network, so we have one hidden layer, but how many neurons? And that's small j will underfeed the data, big J overfits. So how should we choose? Many methods. I did a lot of work on that during my PhD, and after that we have some papers where we use some kind of statistical methods. These methods, they work if you want a small network. Okay? So if your function is able to approximate, being approximated by a small neural network, the methods that I developed can work. These methods are available in these papers. I can discuss about that. Okay, but for large networks, it's not going to work. And we can also use cross-validation. You can use information criterion. This one here, that's an example where I don't like IC because the degrees of freedom are not easily computed. Okay? Cross-validation, on the other hand, too intensive. Okay? Something that I like, Bayesian regularization, okay, which is also being implemented in several packages. I'm going to give you an overview about the topic. Another technique that can be used, like pick a small number and use boosting. So you use boosting to combine small, shallow networks that are poor learners, but when you combine them, you have a very strong model. Okay, or you can pick a large neural network and use some bagging to estimate it. So there are many ideas that can be used on how to determine your neural network. Okay? Or you can do what we call the extreme learning. That's a procedure that I proposed in a book chapter a couple of years ago, and also it's been proposed independently by other authors in the International Journal of Forecasting, and I'm also going to show how this works for you. It's a combination of lasso with neural networks in a kind of a neat way. Okay? So let's see the extreme learning first. So take an activation function as j. Suppose that we have like capital J, that's for each function, each neuron, okay, is defined by this function xj. Okay? And I'm going to reparameterize this a little bit because I'm going to have the linear combination that's going to be given by delta, but this delta is normalized to be norm 1, okay? And then I have this parameter gamma j, because gamma j, we have a logistic function here, okay? So gamma j is kind of controlling how steep is the transition. It can be like this or it can be like that, okay? That depends on the gamma j. Okay? And the new j, if you remember the hyperplane interpretation, this capital delta will give the orientation, the direction of the hyperplane, and this new j will give this distance here. Okay? So we can use this geometric intuition to derive a procedure. So what we're going to do, instead of estimate these parameters, okay, I'm going to generate them at random, but I'm going to generate in a smart way, taking into account this geometric interpretation. I'm going to get gazillions of these neurons, of these terms, of these functions S. And guess what? How I'm going to estimate the linear combination of these gazillions of functions? Lasso or adaptive lasso or adaptive elastic net, something that induces sparsity, such that I'm going to retain only a small number of these gazillions of functions, okay? So how it works? For each unit, for each neuron, okay, and each variable, I'm going to randomly pick a number delta from a uniform between -1 and 1 independently, and I'm going to construct the vector delta j, okay? So the vector delta j will be 1s and -1s divided by the norm, okay? So such that the norm of delta j is 1 by construction. Then I'm going to pick Nij between a uniform between C bar below and C bar above, where the bounds are given by the 5% and the 95% empirical quantile of what? My hyperplane. So here basically I have the data, okay, here distributed in 2 dimensions. I have hyperplane here. Putting a hyperplane there, it's meaningless because there's no data points here. Or putting a hyperplane here, also meaningless because there's no points. So I want like to put bounds that I'm going to test hyperplanes between the 2 dashed lines. Okay? And I can pick as many as you want. And then the gamma j, the smoothness, I'm going to pick from exponential distribution with mean 1. Okay? And I'm going to do this many times. Then we have, remember, a linear method, a model, and then how we estimate. So this will be given because it's randomly generated. And this one here, I'm going to estimate with lasso, adaptive lasso, elastic net. You can use CAD, you can use any method you wish. Okay? Does it work? Let's see. So let's see for a simulation. I'm defining this z variable as an AR1, the x variable as a function of z's, okay, and y is x, the linear term, plus a nonlinear term, plus u. This f bar is a normalized function, and I have many types of functions, 8 different types, from the simplest one that's linear to a very complex one, okay. These are kind of the plots of the functions. You can see that there are functions with discontinuities and weird functions like the last one here. And so let's see how it works. And basically what we look here is 100 observations. Okay, we are looking at the bias, mean squared error, correlation with the true function, and standard error. Okay, for each one of the 8 models. Overall, we have like the 3 techniques about with extreme learning and Bayesian regularization, that the technique that we are going to see in a minute. We basically see that all in all, if you can have summarized, Bayesian regularization do usually worse in terms of bias than the others. and mean squared errors kind of, in some cases, are much worse. But what we can see is that neural networks are doing pretty well, and my randomized procedure estimating things with very, very low bias and small NMC and high correlation with the true function. Apart from some cases here, now even this number here is Bayesian regularization, it's not the randomized one. The last function is kind of difficult, but look, oh boy, that's a difficult function with this spike here, right? Otherwise, it's kind of pretty easy. The correlations are very high, and the standard errors are close to 1, so it looks like a pretty good result. And if we increase to 1,000 observations, we see that the results, like the MSE, drops dramatically. Okay, and again, apart from the last function, all the correlations are pretty high, almost 1. So basically, the technique works quite nicely. Okay. All right. To wrap up, let's look at Bayesian regularization. So Bayesian regularization is basically a reach applied to the neural network, to the shallow neural network, under the assumption of Gaussianity. Okay. So basically, we have two regularization parameters. Of course, we can set lambda 1 to 1, and we just tune lambda 2. That's what is usually done. And Qt is the sum of squared errors. Q star is the penalty. Usually, we are going to use the square penalty, and this is similar to reach. Okay? We have the data set that we call it Y and X. We call M a given neural network model, okay? And we compute the posterior. What's the posterior of the parameter of interest given the data, given the regularization parameters, and given the model? By the Bayes rule, this is the probability of the data given the parameters, the regularization, and the model. The prior of the parameter giving the regularization term on the penalty and the model, and the probability of the data giving the regularization and the model. Okay? So these are the three. So basically, this is the likelihood. Okay. All right. Let's assume that everything is Gaussian. So I'm going to have a likelihood that's Gaussian. The prior is Gaussian. So we can combine things, and this posterior will be a function of the regularization parameters and an exponential times an exponential of the regularization term. And the posterior probability, we want to compute, like to maximize it, like the probability of the parameters given the data and the regularization. It be equivalent to minimizing the regularized objective function. Okay, and we are going to rewrite things by basically computing the posterior of the regularization, because we have to select the regularization given the data and the model. And if we assume a uniform prior for the regularization parameters here, okay, then maximizing the posterior is achieved by maximizing the likelihood function. Okay, and some computation, we put everything together, we get the probability of the data given the regularization parameter and the models, this expression that you see on the slides. And basically, what we can see is that we have an expression for the regularization terms, okay, and we can conduct the optimization in steps, okay. Basically, we initialize lambda 1 and lambda 2 and the network parameters, random choice, okay, and at each estimation step, we recover from the object function parameters are recovered from the initial setting, and then we take one step minimizing the objective function q tilde, okay? And then we can compute, for instance, the effective number of parameters, in this case, using a kind of Gauss-Newton approximation for the Hessian matrix. Okay? So it's like nonlinear optimization of the posterior. And this is done in cycles, iteratively, until convergence. Okay? Then this is the Bayesian regularization, which is kind of very neat estimation procedure. Okay, some food for thought. We can combine neural networks like linear plus neural network. That's a paper that I have with two co-authors. So we have a linear term plus a neural network. So basically what you're saying, okay, start with a linear model. If the linear model is not enough, then you include some nonlinearity. Okay? There's also the neural coefficient smooth transition model, where basically we have a linear model, but the coefficients of the linear model is a neural network. Okay? I have two papers published on that, and it has nice properties in terms of interpretation of the model. So this is just to give you ideas that we can combine things, right? And so neural networks with linear models, with random forests, with boosting, with bagging, you are going to have, by the end of this course, a full menu on possibilities. And then you have to use your creativity to wisely combine these techniques and wisely use them in practical situations. I'll be really glad to discuss these topics with you, and it would be fantastic if you can come to our live session on Friday and we can discuss a lot about that. Okay? Thank you very much. See you in the next block.